Hello, and welcome to this presentation for the Innovations in Theoretical Computer Science conference for the paper Graph Reconstruction via Maximal Independent Set Queries by Christian Konrad, Victor Traistaru, and myself, Conor O'Sullivan. Let's start by setting the problem of graph reconstruction. This problem consists of two parties, a player and an oracle, where the player only has access to the vertex set of an input graph, whilst the oracle has access to the entire input graph. The player is required to learn the edge set and thus the whole input graph from the oracle. And the player can achieve this through making queries to the oracle for which the oracle can respond with an answer for that query. And here we are concerned with the number of queries that the player has to make to the oracle to solve this problem. And we can distinguish between two approaches the player might make with their queries to solve this problem. Non-adaptive queries consist of the player constructing all queries independently of any other query answer. And this way, these queries can be executed simultaneously. We do not have to wait for the oracle to return an answer to construct our next query. And this is quite a preferable approach. Since they can be executed simultaneously, this admits straightforward parallel implementations of these algorithms. Alternatively, the player can construct queries based on previous query answers, and in doing so, we can assign queries to certain rounds, which can all be executed simultaneously, and then queries in the following round are all based off of answers to queries from the previous round. The types of queries that we are concerned with are maximal independent set queries. And this is a novel type of query with no known results for the problem of graph reconstruction. A maximal independent set query takes as input some subset of vertices in the input graph and outputs a maximal independent set in the induced subgraph of that queried subset. And this maximal independent set can be chosen by the oracle adversarially. So for example, if we are given this vertex set V, and we choose to query some subset of this U, the oracle will know the input graph and it will know the edges that exist between vertices in our chosen queried subset. And since an independent set can only contain non-adjacent vertices, the oracle will adversarially choose one of these endpoint vertices of every edge in the vertices contained in this queried subset, and adversarially choose one of these to be included in this independent set. So it might, for example, return this independent set, and as the player, this is what we would see returned from our query. Now note that this excluded vertex in our queried subset, we know it must share an edge between one of the vertices contained in the independent set. But from the player's perspective, it is not certain which of these vertices share this edge. A reason we initiate the study of graph reconstruction using maximal independent set queries is because there are known results for graph reconstruction using a similar type of query, the independent set query. Here, the independent set query takes as input, again, a subset of the vertex set, but this time it outputs a Boolean. It simply outputs true if all vertices in that queried subset are non-adjacent, if they could all belong to an independent set, and otherwise it returns false. And we can see that maximal independent set queries must be at least as powerful as independent set queries. And this is due to the fact that an independent set query can be answered by a maximal independent set oracle, where if we were to choose our subset to be queried and send it to a maximal independent set oracle, just by viewing the independent set returned by this oracle as having the same size as the subset queried, this would correspond to an independent set query oracle returning true. And there are known results for graph reconstruction using the independent set query model. In 2008, Angluin and Chen showed that for the class of graphs that have n vertices and m edges, theta of m log n independent set queries are necessary to exactly reconstruct a graph. We show that with similar techniques that actually, if we were to parameterize graphs by their maximum vertex degree delta, then omega of n delta log n over delta independent set queries are required to reconstruct a graph when delta is of size at least log n. So we know that maximal independent set queries are at least as powerful as independent set queries. So our key motivation is to understand if maximal independent set queries are strictly more powerful than independent set queries. In our paper, we present two algorithms and two lower bounds for reconstructing a graph using maximal independent set queries. We present a randomized algorithm that requires big O of delta squared log n, where delta is the maximum vertex degree, number of maximal independent set queries required for graph reconstruction with high probability. And we present a deterministic algorithm that requires big O of delta cubed log n over delta maximal independent set queries. Both of these algorithms are for non-adaptive queries. We provide a lower bound for all randomized algorithms of omega of delta squared plus log n, and this holds for adaptive randomized algorithms. We also present a lower bound for all deterministic algorithms of omega of delta cubed over log squared delta maximal independent set queries. And this only applies to non-adaptive algorithms. We note that our randomized and deterministic algorithms require knowledge of the value of delta. And if this value is unknown to the player, then we can convert these algorithms into adaptive algorithms that require big O of log of delta rounds of adaptivity, making successive guesses of some integer d until the value delta is reached. We note that for the class of graphs parameterized by the number of edges n, maximal independent set queries do not provide any speedup over independent set queries. This can be seen through our randomized lower bound, omega of delta squared plus log n, which is equivalent to omega of m when parameterizing by n. And so maximal independent set queries in this case are not strictly more powerful than independent set queries on the class of graphs parameterized by n. However, for the class of graphs parameterized by their maximum vertex degree delta, maximal independent set queries are observed to be strictly more powerful than independent set queries. Recall that omega of n times delta times log n over delta independent set queries were required to exactly reconstruct a graph. Here we can see with our randomized algorithm, big O of delta squared log n maximal independent set queries are required. A huge improvement over independent set queries, and thus on the class of graphs parameterized by their maximum vertex degree, maximal independent set queries are more powerful. For our non-adaptive randomized algorithm results, our strategy will be to consider all the non-edges of the input graph, rather than focusing on learning the edges of the input graph. Let's take two vertices u and v that share a non-edge. By querying just these two vertices and excluding all of their neighbors from a query, the oracle will have to return both u and v in its maximal independent set. Since both u and v are returned in the independent set, we learn that there must be a non-edge between them, that they are non-adjacent. And so we say that this maximal independent set acts as a non-edge witness for the non-edge uv. Our method now is to sample many random subsets where the probability of inclusion of a vertex is 1 over delta plus 1. This turns out to be an optimal probability. In this scenario, the probability that a non-edge uv is learned has to be greater than or equal to the probability that u and v is included in our query, multiplied by the probability that all of the neighbors of u and v are not included in that query. Looking at the first term on the right-hand side, we see that this must occur with probability of 1 over delta plus 1 squared due to our vertex inclusion probability. And looking at the second term on the right-hand side, we see that this must occur with 1 minus 1 over delta plus 1 squared to the power of the number of neighbors that u and v might have. This is at most 2 delta, and so we can bound this again by 1 minus 1 over delta plus 1 to the power of 2 delta. This results in the probability that a specific non-edge uv is learned is equal to omega of 1 over delta squared. So our non-adaptive randomized algorithm simply consists of sampling for some large enough constant c times delta plus 1 squared times log n many subsets. In this case, the probability that for two specific vertices that share a non-edge, that they are not contained in some independent set returned by an oracle answer to a query, this has to be less than or equal to 1 over n cubes. And by taking the union bound over all theta n squared non-edges, we see that the probability that any non-edge is not reported in any independent set is less than or equal to 1 over n. So with high probability, we learn all of the non-edges in the input graph through c times delta plus 1 squared times log n many queries. By taking the complement of this non-edge set, we learn the entire edge set using big O of delta squared log n many queries. For our non-adaptive deterministic algorithm, we will use the same strategy that we use for our randomized algorithm by focusing on learning the non-edges of the input graph rather than the edges, and also by constructing queries using the probability of vertex inclusion as 1 over delta plus 1. This way, we can provide an existential proof of a deterministic algorithm using the probabilistic method by showing there exists with positive probability there is some set of queries that reconstruct the graph exactly. To argue that there is a set of queries that a deterministic algorithm could execute to successfully reconstruct a graph exactly, we introduce some helpful definitions. Our first definition is that of a witness. Although we talked about witnesses for our randomized algorithm, it helps to further clarify what we mean in this context. A witness will be the tuple composed of two subsets of vertices, u and v, and distinct vertices w1 up to w2 delta. We further define a delta query scheme. Given a set of queries, Q, we say that Q is a delta query scheme of size L if for every witness, as we have previously defined, there exists a query in that set such that U and V is contained in that query, and W1 up to W2 delta, none of these are contained in the query. And we can then say that a query QI considers a witness W if conditions 1 and 2 hold for QI and W. We now want to show that a delta query scheme of size L can lead to a deterministic algorithm for graph reconstruction by executing all L queries of the delta query scheme. For this to be the case, we need every non-edge to be contained in maximal independent set corresponding to some query in our set. Consider a specific non-edge UV. Since our set of queries is a delta query scheme, there must exist a query in our set such that U and V is contained in that query, and none of the neighbors of U or V are contained in that query. Because of this, U and V must be included necessarily by the oracle in the maximal independent set corresponding to that query. And thus, our deterministic algorithm will observe all witnesses, proving that U and V doesn't exist in the input graph. Because this applies to all non-edges in the input graph, we can conclude that our deterministic algorithm, comprised of all the queries that form a delta query scheme, must learn all the non-edges of the input graph, and by taking the complement of this set, it must learn all of the edges of the input graph. We can now rephrase a result that we had with our randomized algorithm, which is that the probability a non-edge U and V is learned in a query QI, previously found to be theta of 1 over delta squared, can also be considered as the probability that QI considers the witness composed of U and V and all of U and V's neighbors, W1 up to W2 delta. In this case, we can consider the probability that a set of queries Q is not a delta query scheme by taking the union bound over the total number of witnesses that can be constructed times by the probability that a witness was not considered by any query in our set of queries. It suffices for the size of our delta query scheme, and thus the number of queries for our deterministic algorithm to execute, to be of size theta of delta cubed log n over delta. And this provides the upper bound for our non-adaptive deterministic algorithm. Our lower bound result for all randomized algorithms is given as omega of delta squared plus log n maximal independent set queries, regardless of whether they are adaptive or non-adaptive. This is constructed by considering two classes of graphs. The first class of graphs being all n-vertex cycles, and the second class of graphs being all graphs that are connected pairs of cliques that are both of size theta of delta. When considering the class of all n-vertex cycles, observe that for any two vertices we can choose, u and v, their neighborhoods are never equivalent. And this is what distinguishes one vertex u from another vertex v. What we need from our MIS query algorithm is to distinguish all vertices to learn which exact cycle we have. Maximal independent set queries distinguish vertices in three ways. The vertex set is split into vertices that were queried and contained in the corresponding independent set, vertices that were queried but not contained in the independent set, and vertices that were not queried. And viewed in this way, our vertex set is partitioned into three subsets after one query. After further queries, the vertex set will continue to be divided into three sets for each of these, and this forms a tree where each layer in the tree corresponds to query. After a sufficient number of queries, all our vertices will be distinguished, and this corresponds to a depth L in this tree. At this depth, there is at most one vertex in every subset, and the depth that achieves this will be at least log to the base 3 of n. This provides our omega of log n lower bound. For the class of all connected pairs of cliques that are both of size theta of delta, observe that any maximum independent set on any of these graphs is at most size 2, since we can choose a vertex from one clique and a vertex from another clique to be included in this independent set, as no more vertices can be included with these since they all are connected. Since the size of a maximum independent set is at most size 2, a maximal independent set returned by the oracle will also be at most size 2. And so we can only hope to learn at most one non-edge per query. And since there are omega of delta squared non-edges to learn, then this will require omega of delta squared queries. Combining the omega delta squared results with the omega log n results for the class of all n-vertex cycles yields our lower bound for randomized algorithms. Our lower bound result for deterministic algorithms is given as omega of delta cubed over log delta many maximal independent set non-adaptive queries. And this is a factor of delta larger than our lower bound result for randomized algorithms. Now, the full proof for this result is quite technical, and we refer you to our paper if you want to read the full proof. But here in this presentation, we want to offer some insight as to why this factor of delta is present between the randomized lower bound and the deterministic lower bound. We can see exactly where this factor of delta difference arises when we consider the question for the non-edge UV, how many queries contain both U and V? When looking at our randomized algorithms, the expected number of queries that contain both U and V is given by the probability that U and V is in a query times by the total number of queries that we ask for that algorithm. From before, the probability that both U and V are contained in a query is given by theta of 1 over delta squared. And the total number of queries was given by big O of delta squared log n. And this results in O of log n many queries that contain both U and V. But for deterministic algorithms, let's say we consider a non-edge UV that is not contained in any queries of size at most 2. In this case, when we consider the set of queries that our deterministic algorithm will make, let's say queries 1 through to F all contain U and V. Since these queries are greater than size 2, There will always be another vertex apart from u and v that we can choose to include in a witness. In query 1, we could choose another vertex other than u and v, labeled w1, and the same for our second query, and the same all the way up through to our final query. By taking these vertices and constructing a witness of correct size up to 2 delta by including other vertices that have not been considered so far, we can then show that this witness is not considered. This is not a valid delta query scheme, and as such, our deterministic algorithm will not be able to reconstruct the graph. The only way to prevent such a witness from not being considered is to ensure that we have 2 delta many queries that contain both u and v. So in this case, we need f to be at least 2 delta plus 1. Only when this condition is satisfied will all witnesses for u and v be considered by our deterministic algorithm. This is where our factor of delta difference shows up. We need omega of delta of these queries that contain u and v, whereas for our randomized algorithm, we only ever needed O of log n. Since uploading a preprint of our results to arXiv, Michael and Scott have offered improvement on our lower bound results by polylogarithmic factors. These results are presented on screen. They achieve this by identifying novel connections between cover-free families and what we described as delta query schemes. So to conclude this presentation, we have initiated the study of graph reconstruction using maximal independent set query oracles. This is a novel type of query, and there were no known results before this paper. We gave 2 algorithms that both required knowledge of the maximum vertex degree in the input graph delta. We gave a non-adaptive randomized algorithm that required big O of delta squared log n maximal independent set queries to reconstruct the graph with high probability. And we gave a non-adaptive deterministic algorithm that required big O of delta cubes log n over delta maximal independent set queries to exactly reconstruct the graph. If delta is unknown to the players, we can use big O of log delta rounds of adaptivity for both algorithms to find a sufficiently large integer d to replace our value of delta in these algorithms. In doing so, our non-adaptive randomized and non-adaptive deterministic algorithms become adaptive randomized and adaptive deterministic algorithms. We also gave 2 lower bound results for all adaptive randomized algorithms with a lower bound of omega of delta squared plus log n maximal independent set queries, and for non-adaptive deterministic algorithms, a lower bound of omega delta cubed over log squared delta maximal independent set queries. Note that this non-adaptive deterministic lower bound renders our non-adaptive deterministic algorithm optimal up to polylogarithmic factors. And this brings us to our open question. Since there is a gap between the adaptive lower bound for randomized algorithms of omega of delta squared versus the non-adaptive lower bound for deterministic algorithms over omega of delta cubed, is there an adaptive deterministic maximal independent set query algorithm that requires fewer than big O of delta cubed log n over delta MIS queries?